Here we're going to have a shorter video than the last one. We're going to talk about sine law. Now we're continuing with trigonometry as we worked on last week when we worked on our right angle triangles. The difference, that's triangle with a right angle, just as a reminder. The difference is our sine law here, it can work on triangles that are not right angles. So what you're going to do, all of these steps here, I'm not going to show you how to do those because you're going to go over those in class. But we're going to jump all the way down to our sine law. And here we have a triangle. This one's already labeled. You'll notice our labels, we have capital letters to represent our vertices. Those are the points, right? The corners of our triangle. So this is point A, capital A. This is point capital B, and point capital C. So those are the angles, the interior angles. The angle B, angle A, and angle C. The way we will label these triangles, and again, note they're not right angle triangles this time, we're going to label them. If we go across from angle B, we see side B, side of length B. Same thing for A. Go across from angle A, we see side A. And note that these are lowercase letters. Opposite from angle C, I have side C. Those are lowercase letters to represent the side lengths, uppercase letters to represent the angles. Now, it does not matter which angle is angle A, or which angle is angle B, or which angle is angle C. The only thing that matters is that our side lengths are opposite to the angles that are labeled the same way. Now, our sine law tells us, what our sine law tells us is that the sine of angle A divided by side length A is equal to the sine of angle B divided by side length B, which is also equal to the sine of angle C over side length C. Now, since these are true, the other way we can write this, we can use it in one of two ways. We could also write it the other way, the inverse way, which is the side length A divided by the sine of angle A equals side length B over the sine of angle B equals side length C over the sine of angle C. So these are both our sine laws here. You can use whichever one you need. Now, what we can take from this, when we're using it, you'll see that in a moment because we're about to go over it. We only need two of these three parts, right? So we have one part here, two parts here, three parts here. One part here, two parts here, three parts here. We only need two of those parts in order to write an equation. An example is we could pull from this, we could say sine A over side length A equals sine C over side length C. We don't need to write this part if we don't need it. This is true, and you'll see what I mean shortly. So, example A, we're solving for a side length here. Note this is very similar to what we went over before with SOHCAHTOA, but we're not going to use, we're not going to be able to use SOHCAHTOA because they're not right angle triangles. So here we're going to use the sine law to solve for the indicated side length. So here we can label this angle A. Label this angle B. If I'm doing that, then opposite angle A is side length A. Opposite angle B is side length B. Here we're solving for an indicated side length. What we're going to do, because we only have A and B's in here, we're not even going to worry about these parts. What we're going to look at is side length B. So we can either use it in the first form or in the second form. I'm going to choose the second form here because it has our unknown, which is side length B, has our unknown in the numerator. You'll see what I mean later. You can use it the other way, we just have to do an extra step. So using our sine law, we know that side length A over sine of angle A equals side length B over the sine of angle B. Here we can substitute in our known values. Again, we're using the same strategies as last time. We worked with our diagram. Now we're going to our known values. Our known value for side length A is 9 centimeters divided by the sine of angle A, which is sine 41 degrees. That equals x. That's the side length of angle, or sorry, that's the side length of side B divided by sine B, which is the sine of 85 degrees. So I can pull out my calculator right away here. I'm going to pull it out and calculate the sine of 41. So 9 divided by sine of 41, which is 0.66. And I'm also going to calculate x, the sine of 85. That equals 0.99, actually 0.996. And now, again, I can just use my calculator right away here. I have two numbers, one in the numerator, one in the denominator. I can divide those out. So 9 divided by 0.66 equals 13.6. X divided by 0.996. And the goal is to isolate for x. Right now it's being divided by 0.996, so I can multiply it by 0.966, and I can do that to the other side as well. Those cancel out, leaving me with an x on my right side. On my left side, I can plug that into my calculator. 13.6 times 0.966. Sorry, 0.996 is what that should read. 996. And when I put that into my calculator, I get 13.1. Therefore, the side length x is 13.1 centimeters. So we'll use that same strategy for this next triangle here. So we'll label, again, we can choose either angle here. I'll choose this one this time. That equals A. So opposite A is side length A, and meaning that 57 degrees here, that angle is B. Opposite B is side length B. So my sine law, we'll use it in the same form as before. So A divided by sine of angle A equals B divided by sine of angle B. And A, if I'm substituting in, A is x, sine A is sine of 38 degrees, B is 12, sine B is sine of 57 degrees. Well, the sine of 38 degrees, I can do that right now with my calculator, is 0.62 equals 12. I'm going to leave that number alone right now, divided by sine of 57 degrees, which is 0.84. And I can use my calculator once more. 12 divided by 0.84 is 14.3. And I need to isolate for this x. Right now it's being divided by 0.62, so it needs to be multiplied by 0.62. Those cancel out, leaving me with x. And 14.3 times 0.62, I can do that in my calculator as well, is 8.86. So therefore, x is 8.86, and our units here are feet. Perfect. So that's how we solve for side length. Notice each time when we're solving for side length, each time we used our sine law in the form with our side length in our numerator. So side length is on top, right? We used this one. We're solving for side length. What we're going to do is use it in this form when we're solving for an angle. So we're solving for an angle next. We're going to label, again, we're going to start by labeling the angles. So that's A, opposite of A is side length A, and this is B, opposite of B is side length B. It's very important that we label those correctly. If we do not, then our final answer won't work. So we're going to use our sine law in the other form, this form here. So sine of angle A over side length A equals the sine of angle B over side length B. And then we'll substitute in our known values. So sine theta, which is A, divided by side length A, which is 10, equals sine 29 degrees divided by 12.5, which is B. So right away I'm going to use my calculator to calculate the sine of 29 degrees. That equals 0.48. And I can actually use my calculator right away again on these numbers here. 0.48 divided by 12.5 equals 0.039. If I round it, and sine theta over 10. Perfect. Now, my goal is to isolate for theta. Right now, it's being multiplied. Right now, it has a sine function on it, and it's being divided by 10. So first, we're going to deal with the 10. Instead of dividing it by 10, we'll multiply it by 10. We'll do that for both sides. We cancel out on the left side, leaving us with sine theta. And on the right side, we have 0.39. There's one of the zeros missing here. And we know how to deal with this. We did this earlier when we worked with trig. When we're isolating for theta, we'll use our inverse sine function, that's sine -1, on the left side, and we'll use that same thing, same thing on the right side. I'm just going to move this over. Inverse sine. They cancel out on the left side, leaving us with just theta, and we'll use our calculator. The inverse sine of 0.39 is 23 actually. It's 23 degrees. Therefore, theta is 23 degrees. That's our missing angle there. We'll use this same strategy, again in the same way, and we'll label them. So I can choose to label these as I wish. So I might choose to label the 36 as A and theta as B, but that means how I label my angles tells me how I need to label my side length. So opposite of B is side length B, and opposite of A is side length A. So we can use our sine law. Again, we're using it in this form here. Sine of A over side length A equals the sine of B over side length B. And then we can substitute in our known values. So the sine of A is the sine of 36 degrees. Side length A is 9. And sine B is sine theta, divided by side length B, which is 15. So as we did before, we're going to calculate the sine of 36 degrees. That's 0.59. Still divided by 9 equals sine theta over 15. Again, we can throw it right into our calculator once more. So 0.59 divided by 9 equals 0.065. And that equals sine theta divided by 15. As we did before, when we were trying to isolate for theta, first we deal with what's in our denominator. So instead of dividing by 15, we'll multiply by 15. These will cancel out on the left side, leaving us with sine theta. Sorry, on the right side. And on the left side, we can throw that right into our calculator. That's 15 times 0.065. That comes to 0.98. And then we can do like we did before, is use our inverse sine function. Sorry, that was a bit ugly. We'll use our inverse sine to isolate for our theta. We do it to the right, so we need to do it to the left as well. The inverse sine of 0.98 is 78 degrees. Our sine -1 and sine cancel out, leaving us with theta. So therefore, theta is 78 degrees. Perfect. Now, when do we use our sine law versus our primary trig ratios, which we used all of the last week we're in here, which was SOHCAHTOA? Well, as I alluded to at the beginning, we'll use our sine law if it's not a right angle triangle. We'll use our primary trigonomic ratios when there is a right angle triangle.